Hey guys, in last video I introduced the Cauchy Criterion for uniform convergence and I said it will be quite useful in proving the force property of the uniform convergence sequence, right? So in this video I will first show you the proof of Cauchy Criterion and the theorem we mentioned in last video. So first of all, I feel like well, let's first recall the Cauchy criterion. It's actually sufficient and necessary theorem, right? It says, well, because it says if and only if. So um, but I'm not gonna show you the necessary part because it's quite simple. If you are given a sequence of functions, a sequence of uniform convergent functions, simply use, if I have to give you a hint, simply use the triangle inequality. Will give you the answer of the which is the inequality. So it's quite straightforward. So I'm not gonna show you in this video, but I'm gonna show you the sufficient part. So now we are assuming that we have the inequality already, and we want to show that the sequence of functions is converging uniformly. So what we first do is to produce a candidate of the limit function. And since we are creating that candidate of the limit function, we will have the function itself will have some properties since we are creating it, right? And of course, it will satisfy the inequality. So we first produce a candidate for the limit function, and then we will prove that the sequence of functions is actually converging to that candidate function. So, well, first of all, we already have the inequality, right? So the first thing I will do is that, well, since we know that for any mn larger than n, we have fn x minus fn x, take the absolute value of it, will be smaller than epsilon. Then actually you might observe that fn x is actually a Cauchy sequence, right? And I remember I said before that a Cauchy sequence might not necessarily convergent because the limit sequence, the limit function might not be in that set. But in this case, for simplification, we assume that the limit function will be in that set because actually the difference between Cauchy sequence and the Cauchy sequence and a convergent sequence are quite subtle. So here we just for simplification, we just assume that this Cauchy sequence of functions is convergent, right? And it is under the D1. Yes, it's D1. D1 this distance. So we will have limit fn x goes to fx, right, for each x in A. So what this equality tells you? It tells you that fn x actually pointwise. Fn x actually converge pointwise to the candidate function fx, right? The function, the limit function of fn is the candidate function that we're choosing. And actually, you know that we will show that fn is going to uniformly convergent to f, so it must converge pointwise to f, right? So this is I feel like in this case, to find a candidate function is quite straightforward. So, okay, and then we know that still fnx minus fmx is larger than minus epsilon and smaller than epsilon. So if we take the limit of this function fmx, and well, fnx is actually the same thing, right? So it will go into fx, right? And so now the inequality becomes fnx minus fx is smaller than epsilon and larger than minus epsilon, right? Because epsilon doesn't have any connection to epsilon will not be affected by taking the limit of n or n, right? So actually, if you take the limit of fnx, it's the same. Just keep fnx unchanged. So then, after we know this inequality, then the consequence is quite clear. Fnx is uniformly convergent to fx, right? Because this is valid for any x in A, and for all n larger than capital N, right? So this is a proof of Cauchy Criterion for uniform convergence. So now let's move on to the fourth theorem. It says, okay, so first of all, the theorem says that let fn, the sequence of functions fn are all differentiable in AB. So in fact, fn are all continuous in AB, right? Differentiability can conclude continuity. And then we suppose that there exists some point x naught in AB such that fnx naught is convergent. Fnx naught is now a sequence of values, right? Because we have fixed an x naught. And if there exists some function g such that f and prime converge uniformly to g in AB, then we will have, first of all, fn goes to f. Fn converge uniformly to f. And the second conclusion is that for any x, f prime x exists and f prime x equals to gx. So the way we prove this theorem is a bit tricky. I actually have written down the proof of it. So let me first clarify that the idea of this proof is to first find the function g. In the condition of the theorem, it says if there exists g such that fn prime uniformly convergent to g. So we first find such function. We kind of like construct a function, kind of like construct this function, but we know that, but in a very like obvious way, because we know that fn prime uniformly convergent to g, right? We first construct this function, and then we show that fn, the sequence of function uniformly converge to the limit function f. Okay. So as I've written here, first of all, we want to show that for any say in AB, f prime say is equal to limit x goes to c, fx minus fc over x minus c. This part is a definition of the derivative of f, right, at c. And so here we wanna like include the sequence of the function, but actually we are so this is a definition f prime at c, and we wanna introduce the sequence of the function. So we like further expand it as limit x to x goes to c, limit n goes to infinity, fnx minus fc over x minus c. So this is what we want to show. Suppose we have already shown that fn goes to fn uniformly converges to f, then we will naturally get this equality, right? So what we will do is that we define gnx. Gnx is equal to, if x is equal to c, then gnx is equal to fn prime c. If x is not equal to c, we will have fnx minus fnc over x minus c. So this is gnx. And we show that gnx is uniformly convergent in AB, right? Uniformly convergent to G, right? So when x is equal to c, gnc is definitely goes to gc, right? Because gnc is simply equal to fn prime c is how we define gn, and then fnc goes to gc because we have fn prime uniformly convergent to g. Okay, and for x different from c, we want to show that here gmx minus gnx, taking the absolute value of it, will be smaller than epsilon, and this is where we use Cauchy Criterion, right? So first of all, let's see the left hand side. So left hand side, if we write it in the definition, in how we define gnx, it will be fmx minus fmx minus fmc over x minus c minus fnx minus fn. This should be fmx minus this is the right way, I'm sorry. fmx minus fmc over x minus c and fnx minus fnc over x minus c, right? Yeah, no problem. And then we rearrange the order of the terms, we will get fmx minus fnx, term 1, minus term 2, fmc minus fnc, right? And you see the similar pattern, fm something minus fn something. So we substitute fmx minus fnx into hx, right? So all we got is the left hand side now equals to hx minus hc over x minus c, right? And all the functions here are continuous, right? Because fn are differentiable. Everything here will be continuous. So we can use the mean value theorem. Mean value theorem says that this equation will be h prime x1. x1 is between xc, suppose x smaller than c, or cx if x is larger than c, right? So there will exist some point like x1 such that hx minus hc equals to h prime x1 times x minus c, and x minus c cancels out. We will get h prime x1. h prime x1 will be equal to f prime m x1 minus fn prime x1. This is still because of the continuity of all these functions. Okay, and this term will be smaller than epsilon, right? Because fn prime is converging uniformly, right? I'm sorry, I said before that I want to show gnx is converging uniformly to g, right? well, it's not wrong. Gn can converge uniformly to G. Yeah, that's true. That's true. I'm sorry. I thought I said something wrong, but okay. This is not the end of the proof, right? This is not the end because we haven't shown that Fn is converging to F uniformly. So now we're taking C equals to x naught. X naught is the point defined in the theorem. It says that suppose there exists, remember that? Suppose there exists a some point x naught such that Fn x naught is convergent. Taking C equals to x naught, we have Fn x equal to Fn x naught plus x minus x naught times Gnx, right? So now we can use that fmx minus fnx and use Cauchy Criterion to show that this term will be smaller than epsilon. And to expand fmx and fnx, we get fmx naught minus fnx naught plus, this is term 1 and term 2, oh I'm sorry, should be this line, fnx naught minus fnx naught plus x minus x naught times gmx naught, gmx minus gnx, right? And it will be smaller than, or because this part will be smaller than b minus a, right? So the whole equation will be smaller than fmx naught minus fnx naught, and we're using the since Fn x naught is convergent, right? Fn x naught is convergent. It's a convergent sequence. It's a convergent sequence of values, right? So you can say that it's smaller than epsilon, and this part will just prove that it's convergent uniformly. It will be smaller than epsilon, and this is b minus a. So actually it will be epsilon plus minus b minus a times epsilon, right? And we want to make it like look more like the way we define the uniform continuity. We can actually say that we take this epsilon to be b minus a over a half of epsilon. Say it's epsilon 2 and this is epsilon 1, and this epsilon becomes a half of epsilon. So the final inequality will be epsilon over 2 plus b minus a times half of epsilon over b minus a, and this will go to epsilon, right? Equals to epsilon. So we show that the sequence of functions Fn is convergent uniformly, right, on the set A by Cauchy Criterion. So we use Cauchy Criterion twice in this proof. So I think this is what I want to show you in this video. So I will see you in next one.